Okay, so it's going to be me at data-oriented programming in Java with a strong focus on Java 21 specifically. Since I already had you raising your hands, who of you is running Java 17 in production somewhere? Who of you has Java 11 as the newest version in production? Java 8? Should I go lower? I'm going to spare you the embarrassment, okay. Who's going to update to Java maybe 21 over the next year or something? Wow, great. That's what I want to see. That's amazing. Okay, so I'm going to show you, Java 21 is full of good stuff. One big half is what we're going to talk about now. Another big half is virtual threads. And then there's a third big half, which is everything else, because there's even more in Java than just these two big topics, in Java 21 specifically. But we're going to start with this concept of data-oriented programming. The slides are already online. If you go you know the volume, what is this? Thank you. Because I tend to speak quite loudly. If you go to slides.e5x.dev, you will see the slides online on the right-hand side, and you can already follow along if you want to. So we're going to talk about data-oriented programming. I'm going to start with the definition that is somewhat useless. And then we're going to have a lengthy example where we apply out those steps, and then we have a little retrospective at the end to see what we just learned. So let's start with what data-oriented programming is, or specifically, or more generally, what programming paradigms work. So usually programming paradigms, more or less, come with an everything is the sentence. And the goal of every programming paradigm is to manage complexity. It's always about the evolution of your system, of your business requirements, of dependencies, of those various ways that pull complexity into your solution and how to manage that. And nowadays, all modern programming paradigms are good. None of them are terrible, and none of them is just generally better than another one. Functional programming, object-oriented programming are two big ones. They have their own advantages and disadvantages, and so you should really ask which one is better. The answer would be it depends. But that's a cheap answer, because if you stop there, everybody can say it depends. So what I'm trying to do today is trying to tell you what it depends on for when you want to try out data programming. So as an example, let's start with object-oriented programming. Probably the programming style that we're most used to. In this talk, this will be the default for which we set out to learn about data-oriented programming. The hallmarks are providing state and behavior, to use encapsulation to hide that state, and then to use polymorphism, to use inheritance to express polymorphism. So when I say polymorphism, what I mean is to have behavior that follows a shared contract to be different in implementation depending on the data it works on. We all know that intuitively, even if you don't know the term polymorphism, you know what you call add on a list. It does the thing, namely adding an element to a list, but the implementation is very different within a linked list versus within an array list. So it behaves differently depending on the type it's operating on, and that's implemented through inheritance because the list interface has an add method that gets a lot of business implementations in different classes. What already just arrived? There are a few seats here in front. I promise I won't bite. Just come up, sit down, grab a good seat so you don't need to stand. Did somebody kick out all the Java developers off another talk? Object orientation works best when it's about maintaining boundaries. When you have a large problem and you want to turn it to smaller problems, so focus on each small problem to find a solution. So boundaries between sub-problems, boundaries between your code and your dependencies, boundaries across versions. That's where object orientation really shines. Therefore, as I said, boundaries between libraries and clients, other cases, therefore object orientation is great. But the smaller the problem gets, the less benefits you get out of object-oriented programming, but you still have the data applies by isolation and inheritance in the direction. So a smaller subsystem that is mainly focused on handling data, that's where I want you to consider a data-oriented programming approach in the future. So what is data-oriented programming? In an article in 4Q that's called Library for, but flagship by folks, called like the article, Brian Katz used the Java language architect wrote that article. we put forth these four guiding principles. Model the data, the whole data, and nothing but the data. Data is immutable, validate at the boundary, and make legal states unrepresentable. And if this were a 5-minute lightning talk, I'd now go on stage and say, this is data programming, have fun. That's what I meant by giving you like a guideline or definition. It doesn't really help. We'll see afterwards how this all plays out. So let's go with this example, and let's apply this step by step and turn something like an object-oriented solution into a better data-oriented solution. So the code that I'm showing you here does exist online from my GitHub. It's in Loom Lab. That might be a little bit worthwhile. It's a little bit confusing maybe. I'm going to show you in a second why that is. This is what this little program does. It's GitHub crawler. You give it a URL, GitHub URL, connects to that, that identifies what kind of page is it. Is it a pull request page? Is it a issue page? Then looks for the interesting section in the middle, the conversation, not the header, not the footer, pulls out more links, and then connects to those links and starts again at the top. So it just trawls the GitHub code here, it didn't give you the depth, so it doesn't crawl all of GitHub. And it stops when it reads an external page. So when it finds that you link to Wikipedia, it stops crawling there, doesn't call the internet set. Now, all of that logic is done in this method. It uses virtual threads. That's why it's in the Loom Lab repository. But we don't care about that here. We don't care about how this works internally. What we care about is this return that it gives. It returns a page, an instance of the type page. And now the question that we're going to focus on is, what does page look like? So the crawling already happened, basically. We're now looking, okay, what's the process after that? So let's gather some requirements. All pages have a URL, and if the page could not be resolved for whatever reason, it contains an error. But if it could be resolved, it contains some content, like a interesting section in the middle that I mentioned before. And if it's actually a GitHub page, it connects outgoing links, and if it's an issue number or pull request, so it's an issue page or pull request page, it pulls out those numbers as well. You know, not that we have like this little graph of GitHub pages of a specific project, we could do all kinds of things. Right? We could display them as interactive graph. Since it is a graph, we can put graph properties. We could maybe categorize pages by topic. Maybe we want to analyze the moods of the project, or want to for all this as features in our application. Maybe we want to have tables as well for that, so we process data for that. This is all very hypothetical, and none of this is in the app, because that's actual work. It's a demo app. It does nothing useful. What it does is evaluate some extremely simple statistics, and it creates a pretty string. And so that's actual the operations I'm going to show you, because those fit on one slide. Now, how would you implement that? The naive object-oriented approach would be this. To take a class or page, and then you give it all the properties that were shown earlier. It can have an URL, it can have an error, it can have content, issue number, pull request number, outgoing links, and then you can stream like a subtree in this very specific thing. Now, you could think of this as called get URL and get error, get content if you prefer getter. I don't like the get syntax, and if you catch me later after my talk is over, I'll happily tell you, or as long as you let me, why that's a bad idea. But for most classes, I prefer to just call it URL and not content without get. But these are just simple accessors to underlying data. And at the bottom, we have two actual methods that we want to have, evaluate statistics, and something to participate. And you can do that, right? You can write that class, you can put everything that we, all the requirements we just gathered for this one type, and off you go. That's not a good implementation. And even with object orientation, there are better approaches. The biggest problem is that the page type is implicit. When I say page type, what I mean is that we know that we either have something that was error, or that connected to GitHub. And if it connects to GitHub, we know it's either a pull request or an issue page. We're going to ignore that because there's more than that for now. So we know that there's some kind of constellation of data that's better than other constellations are. You cannot connect one of those pages and have a GitHub pull request number and an issue number. There is no such page that doesn't exist. But the type effectively allows this. So the kind of page that we have is very implicit. You have to guess by accessing some of the fields, like what combination do I have here. That is bad for all the opposite type, but it's also bad for twice of the type because they also do this guesswork. And you have very different operations on the same type. The food operations that we actually do have on the type, the statistics, and the pretty, those are very simple. But imagine again that we have all these other operations, right? Painting something on a 2D canvas and processing payment are very, very different things. They deal with entirely different subsystems. You do not want these methods on the same type, because if that type knows the payment processing subsystem, then it knows the catalyst, and it knows the graph theory aspect of your application. And that just means you have this type in the center of your system that knows everything else in the system. That's not good design. That leads to a card class becoming too large to compartmentate. So let's start. Let's apply data object programming principles. Model the data, the whole data, and nothing but the data. That was the first, and probably the key guideline. We're going to focus on the first part for now. Model the data. What's the data? Well, we have 4 kinds of pages. We have an error page. We have an external page, like if we ended up at Wikipedia or wherever. And then we have a GitHub issue page or pull request page. So, let's use 4 types of this. And specifically, let's use records. So in case you didn't know, everybody raised their hand at using Java 17. I'm pretty sure you've used records a lot, just because they're that much fun. And just still to writing much less code, they get more functionality for free. And that's good, but that's not what records are about. Records are transparent carriers for immutable data. And then they're transparent in the sense that the external state and the internal, like the external visible state, observable state, and the internal state are tightly coupled. So the compiler understands the internals and couples the API to the internals. And that's why you get everything for free, which you get, we're not show on the next slide, but you get hash code and it equals and constructors all that for free. But the goal of records is not to give you this code for free. The goal of records is to model transparent carriers to immutable data. There's a consequence you get that stuff for free. And I'm highlighting that because if you're thinking, oh, I want to save some boilerplates, I'm going to use a record, then you soon going to run into limitations of records that are going to make you very unhappy. Because why can't I have this hidden field? It's just like it will help me reduce boilerplate, yes, but that's what records are about, transparent carriers. We want to see that transparency becoming important later. This is how we look for define some kind of one kind of record. So we have a record called external page, and then this is the record. It says record, but we usually say class or interface, right? Then it says the type name, and this is entirely weird because that does not exist in Java before. What you put here is called components. So put a list of components into the definition of a record. And that's it. And this is the body of the type. This is where you usually put fields, constructors, methods. But you can't put much of that here, not fields, but you can add additional constructors. You can implement interfaces, you can add methods. But if you don't need to, you don't have to. This is a better type. What you get is external page to final, is that it has private final fields for the URL and for the content. You get a constructor, which looks exactly like this. It takes these 2 arguments. You get the accessors with equals hash code, bar 1 of it. And you can customize the bodies of all this. Okay, so let's use this. Let's model all the data. The external page was the one that we just built. It has URL and content. This error page has a URL and exception. Let's get an issue page. It's a URL and content, and then also the issue number and some outgoing links. And the pull request page is very similar. It has a pull request number instead of issue number, but also URL with an outgoing links. So what we're doing here is we're thinking about what does the data actually look like? What does the GitHub issue page that we want to represent actually look like? And then we create a type that models the data exactly, without any additional fluff, without what this other kind of page. Now we also brought that in. No. And if it comes to it, repeat yourself. All of these have URLs. Doesn't matter. Repeat yourself. We're going to build some abstraction all of them later. Now, model the data, the whole data, nothing about the data. You could argue that we didn't model the whole data yet. Because one thing that we forgot about, that we didn't look into yet, is that these types have some relationships. Now we built 4 types, but they're standing there, each on their own. But they do have some relationships. The page load is either success or it's not. And if it's a success, it's either a GitHub page or external page. It's a GitHub page, either there's a pull request or issue number. Again, we're going to ignore that GitHub has more pages than that. And for these alternatives, we can use CS types. Now again, if you're on 17, you might already have used CS types, but I kind of doubt it because you can't really do very much with them. CS types allow you to limit inheritance by only allowing specific subtypes. You can have CS interfaces and CS classes, or what a core CS classes strip that's only focused on CS interfaces. What you can do is you can say this interface has these end implementations. I'm going to name them, this and this and this, and that's all the implementations that there are. This communicates this intention to the developer, to your colleagues, but also allows the compiler to check exhaustiveness. We'll pin into the word exhaustiveness, but I'll come back to that later. For now, let's apply this. As an example, we're going to create a CS interface page that permits the type error page. That's a record, we already have that. It also permits the type successful page. We don't have that yet. We're going to create those soon. Now only error page and successful page can implement or extend page interface. So if somewhere else in my code base, or anybody else's code base, I like interface like page extends page, that doesn't compile. The compiler tells me, well, look, you told me only these two types can implement page. This new type wasn't in the list. You can do this. Okay, let's apply this. Let's create some SID interfaces. A page permits the true implementation is error page or successful page because only these two things can be a page. There's nothing else there. If it's a successful page, it must be an external page or a GitHub page. And if it's a GitHub page, it must be a dish2 page or a PostgreSQL page. Because these are interfaces, I'm adding a few properties here and there. I'm adding the URL at the top. Every page is URL. Once it was a successful page load, I know I have some content. Once I have a GitHub page, I know I have outgoing links. I can create this default method that builds the substring. Put this into this handy type diagram. This is not proper UML. But everything that's blue is a sealed interface. Everything that's orange is a record. The important part about this is, you know these inheritance hierarchies, right? But usually inheritance hierarchies are old. You have the collections interfaces. You know this inheritance hierarchy of the collection framework interfaces. But you can plug in your own stuff wherever you want. Like you can grab a list implementation, you can create your own set implementation. You can create a new interface that inherits from a collection. That's whatever you want. This is not the case here. This is a sealed hierarchy. So if you have a page, you know it must, for example, one of these two possibilities. Or you can resolve this further. You can say that a page, it must be one of those four types. And these four types, they're all final. They can also not be further extended. That's important because that models another property of the data, which is this exactly. If I know when I write the program, I want to connect to GitHub pages, I know this is all the types that I have, all the types that make sense. Let's go to the next step. Make illegal states unrepresentable. We already made a lot of illegal combinations unrepresentable. In the original type, original object-oriented solution, the native one that I showed you, you could have a field pull request number that is 5 and a field issue number that is 8. That made no sense, having both of those in the same instance. Now this possibility doesn't exist anymore. There is no such type that has issue number, pull request number, or that has an error at content. So just by creating the types to match exactly the data that we're expecting, these illegal combinations are not impossible anymore because there's no type representing them. But there's a little bit more, and the rest want to validate the boundary. So for example, if we have other states that we consider illegal, we want to make sure that the constructor rejects them. Now, if you have used records before, you might recognize this as a compact constructor. If you have not used records before, let me briefly explain. Now, this is called a compact constructor, and as you can see, it has no parameters. And the reason for that is that a record always has a constructor that takes all of these parameters. And the compact constructor is that one. It takes those parameters. And once your block of code ran out, it assigns them to the fields. The idea by the compact constructor is you really only put the code in that you actually need to write yourself. You don't need to repeat the parameter list that in most types you have 2 lines above. Right? You start with the record definition at the top, and then the primary constructor comes next. So the list is right there. And then also, after that line of code, with assignment to the fields happens, you don't have to do that yourself. That can be done automatically. So all we do here is really just do the validation, check those things that we need to check. And in this case, I want to check that the URL is not null, content is not null, and also that the content is not blank, so it's not empty. So it does not consist only of spaces, for example. Whatever that is for your data, the goal here is to validate that in the construction. And if it's too complex, maybe you have a factory method that checks these properties. The goal is that you not allow the instantiation of this type that models illegal data that should not be present in the system. So when the data comes in at that boundary, you want to make sure that everything works fine. The last one is data is immutable. Now records are already shadow immutable. What I mean by that is that you cannot reassign a field. Right? When you have a private final field, you cannot assign a new instance to that field. So you have this immutability on that level. But the instance in the field itself might be mutable. Right? If you give the user a list of addresses, and that list is an array list, even if it's a private final list field for addresses, everybody who gets the list can still add stuff. because it's there it is, and it's mutable, right? So if you really want to insist on mutability, and that should be the default, you need to make sure that you have immutable instances as far as that's not always possible, right? If you have a mutable user instance and you reference the mutable user instance, there might be very little that you can actually do. But in this case, my links are a set. So what I do is I do a copy of the links that I get. So again, it's a callback constructor. It gets the links in, and I create a set copy of it, and this copy of creates an immutable instance. The details are not that important. What's important? By default, you want everything in the record and below to be mutable, and sometimes you have to start working about calculations that. Much later, we're going to see an instance, show an example, where actually I do want mutability, and then I make sure that that's the basic. Okay, let's catch up for a second. Where are we? We took our understanding of these different kinds of pages that I want to model, and turned those into types, the type system. We made sure that only linear combinations of fields are possible and that everything else is rejected at the boundary. I would play this API as much more self-documenting than the other one. The other one was one class page with a ton of fields, and then you have to tell people which fields work together and which don't. And again, that's a solution. There are better object-oriented solutions. But just for contrast, this is very, very detailed. Like you have a record that's, it's an external page. I have to there's hardly anything to document or even to test. Right? Much of this is just ending in data, and there's a null checking constructor, and that's it. That's really to test. But we didn't discuss that yet is the operations. Where do the operations go? This, I do not like about these principles that Brian put forth. I think this one is too implicit. Basically saying that nothing but the data part is the part that expresses that you should not put operations on these types that do not deal exclusively with that data. So if you have operations that only work on derived quantities, so for example, only create derived quantities. So for example, they have a record name, that is a first name and a last name. And you want to have a method that returns first name space last name, or you want to have another method that returns last name, comma, first name. That's clearly great addition to the record because it just deals with record fields. But if you have something like, draw it on campus that deals with a subsystem, that does not anymore just deal with derived data. So in those situations, you want to put the methods elsewhere, operations elsewhere. Now, unfortunately, again, because the examples that you fit on the slide need to be explained in a couple of minutes, the two operations that I created actually do work as derived quantities. These will not need to be methods elsewhere. Let's pretend. Let's pretend we would have to put them elsewhere. So we have something to play with. So we don't want to put the operations on those types. The operations are elsewhere, but they still need to operate on the data. And now we're using two things that work very well. One of them is pattern matching over serious types. That's great to apply polymorphic operations on data, meaning to apply operations that differ by type. So we're going to see over the next slides how exactly that works. The other aspect is that records do not insist on encapsulation. Right? Records allow with easy access to all internal data, so everything that we need, we can access. That's the second pillar here. Again, we're going to see how that works out. Let's start by working our way towards pattern matching. Let's start with type methods. Type methods put a type check, a cast, and a declaration all in one. So if you take instance of checks before Java 16, you would have written if some kind of instance. There's an instance of GitHub page, and then in the if block, you say, create a new variable of the type GitHub page, and let's call it GH page, and then assign the old variable and do a cast. So you do three things. You do the check of the type check in the if up here, and in the branch you do declaration, and then you do the assignment. And these three things, the check, declarations, and assignments, that's what patterns do. And so type method does all this in one go. If the root fetches into a GitHub page, then declare a variable of type GitHub page with its name and do the cast. And only where the check is passed can I then use GH page. Now, if you now feel like a cold shiver running down the spine because of turning the instance of checks, that's a good reaction. We're going to resolve that. Stick with me for a while. Let's focus on flow scoping. Only where the check is passed is GH page in scope. You can build some funny things with this. So for example, you can say, if the root page is not an instance of GitHub page, then in here, GitHub, that the check is wrong, right? Check is false. So in this if block, I cannot actually use the variable. The compiler understands that the check is negative here. But then I return it and go out of the method. And that means once I arrive here, the variable is actually in scope. And down here, you can use GH page. Now, I'm not recommending if you write code like this, even though I occasionally do, but I don't write code for large teams, so nobody careful, right? I'm showing you this so you understand what it means that something is flow scope, because this will be a recurring thing with patterns. Flow scoping means you do a check, and wherever the compiler knows the check is true, that's where you can use those variables. And sometimes that's obvious. With an if instance of check, clearly in the if branch it works. But if you do an if not check, and then, I don't know, throw an exception or return from the branch, then below that it works. So, flow scoping becomes more important in Java. And already, it's not a new concept, by the way. Flow analysis is kind of old. If you have a private final field, the compiler will insist that you assign this during construction. Like maybe you see that if you're a private final field and you don't assign it, the compiler is mad at you. If you compile it in an if branch, the compiler is still mad at you because it understands that this is a cycle that will happen in all cases. You also need to assign it in the else branch. So the compiler already understands this concept of where's the flow going and what are variables assigned and when are they not. And this is repurposed in this Scholar FQ. Now, since Java 21, this is the big thing. That's why this is so important in Java 21. Now patterns work in switches. This feature has been in preview for a long time, but preview features can still change. So I recommend not to write a ton of code on top of a preview feature, because if it does change, you have to rewrite all that code. So since Java 21, that feature is final, it can now be used, and that's why 21 is so important. This is so important in the context of file. So if you switch over the page type here, you say, in case it's this type, do something. In case it's this type, do something. You know what? You can use the variables PR in the case branch where it works. So that means conceptually, that's not the implementation, but conceptually, it takes the page, it does a linear instance of checks, it finds the right branch, and executes the code on the right with a new variable. Okay, let's apply this. This is just a setup code we need around. Let's skip this, you can look at this later if you're interested. This is the most important part. I get an individual page. I now want to evaluate that page. I have some number of fields lying around that I want to increment. So I'm here, okay, let's go back to the slide briefly. There's a class called statistician which does this, right? So there's a class statistician that counts statistics on this page type, of this page tree that I'm getting. And it does that by distinguishing these types. It says, okay, in case the page is an issue page, I want to increase the number of issues variable. If it's a pull request page, I want to increase the pull request number, and so on and so forth. So it goes to this list of instance objects to find which field to increase. You see how this happens externally. If this would be a method on the page type will say, and I will get some object that will say, I'm an issue, so I'm increasing the issue counter. Or I'm a pull request, so I'm increasing the pull request counter. So the type will know, I'm this specific type, I'm doing this specific operation. But we're not doing this on the page type, we're doing this from the outside. So doing this from the outside means we have to distinguish by type externally and then pick the right variable to increase. Printing works pretty much the same. Again, we have a setup method that gets a page tree and then does, in the end, a create page string method on which gets a page. Again, I'm not repeating myself, but I know it's not trivial. So I will say one more time. You could see how page could have a create pretty string method, right? There could be create pretty string on page, and then it levels every issue page. I'm going to return this. And if I have a pull request page, it returns this because the type knows which type it is on its own. But we're doing this externally. So again, it doesn't do it from the outside. We have to split up the type. We have to type check the instance of page and see which type it is. And left to it, say, look, in case issue page, I'm going to call issue #issue number. And that's really interesting because page, the super interface, does not expose the method issue number, because not every page has an issue number, or an issue page has one. So this method will not be available on the page. I have to actually do this cast where if it's an issue page, I get a new variable of that type that I then can call this method on. And we can simplify this a bit with record reconstruction patterns, so we're going to do that. But this is like the most important slide, because what it does is it tells you I can get an instance of this page type, which I do not know which subtype it is. I can go through all possible subtypes, and then I cast to that, and then I can do operations that are specific to that type, so create by, design without. And now we can look into why this is more maintainable than it might look like. First, we go into how we can simplify this code or change this code a bit. But that's good and important, but it's not as essential as this. Okay, let's keep going. Let's use record patterns. Record patterns, because records are transparent, I told you we'll get back to that, meaning they do not encapsulate their kernels. Every field they have is exposed to the outside world, or there's access over every field. We can take a record apart in this pattern. So we have a record external page that has these two components. In this case label here, we can say, in case it's an external page, and this is entirely new in Java, take it apart into its components, URL and content, and I use bar here to show you that it works. You could also put the types here, of course. So take it apart into its constituent components, and then comes the arrow, and then use those components directly. So you don't have to sit on page type. You can say, I actually care about page instance, the external page instance. Just take it apart on pieces that I need. So that could look like this. I take the GitHub issue page apart into its 4 components, which is quite a lot of code, unfortunately. But then I can reference the issue number directly here. Now, why would I do this? What's the advantage here? First of all, this adds a bunch of stuff, right? Because now I'm taking apart the URL, the content, and the links, all of which are unused. We'll hope that. But why would I even try this in the first place? My answer would be so that you can see on the left-hand side what is the information that you care about. And then on the right-hand side, which on the slide is below, slide's extra. So on the left-hand side of this arrow, you see what do I care about. And on the right-hand side, you see, okay, what do I do with this information? So you don't have the left-hand side, that's this type, on the right-hand side, follow-up exercises. You have on the left-hand side, this is what I care about. On the right-hand side, you just use it. Let's use unnamed patterns. Those are a preview feature at 21. If you update Java 21, everything else I showed you so far, you can use. Nothing's going to change about that. This feature might change. It's not very likely. It's supposed to be finalized in 22 exactly as it is now, but it could be. So you can replace variables you don't need with the other support. You can say, I don't care about this, I don't care about that. All I care about is the issue number. And that's what I do. In case it's a GitHub issue page, ignore everything else and give me the issue number. And if I apply all that, it looks like this. And now mentally reformat this. Again, if I don't have a slide, I'll have 140 characters in one line. And then I could put this on the right-hand side here, right? And this would go here. And then what we would see is, so what does create bridges do? It gets a page. It looks over the page type. It's issue page, I just need the issue number. And then it does something with that, and if it's an external page, only URL. So these text labels already tell you what's going on. I care about this type, and I care about this information of that type. And then the right-hand side does this putting together. If you're used to writing stream pipelines or reading stream pipelines, it's similar in the sense that when I read a stream pipeline, I often start by just looking at the operations. It's a map, it's a filter, it's a flat map, to get like, what is it generally doing? And then maybe if I'm interested, I look on the right-hand side and see like, what are the actual lambdas to it? What do I map from here to there? So you can have a little more distinction between the structure of the code and the actual logic, the business logic of the code. Okay, so looks good, I think that's good. But is it switching over types bad? Right? Instance objects are bad, capital T bad in object-oriented programming. Why? I'm waiting for you to tell me. Why is switching over types bad? And yes, I'm immediately going to say, haha, I'll fix this problem now. So it's a trap, but still. Any idea?
To increase another type.
Yeah. Exactly. Exactly. If you add another type, if you have like, if my list is an array list, if it's instead of array list, do this, instead of linked list, do that. That's all great, but once I get a third type of list in my instance objects, what does the code do? I don't know. Maybe I was lucky enough to put like an else branch that throws an exception, and maybe my tests cover that. But other than that, it's not great. It's not maintainable. It's really hard to find all those switches or instance objects. So that's why it fails in unpredictable ways when you add a new type. That's terrible. That's why we say we shouldn't do this. That's the main reason we should do this. You could make, aesthetic arguments, but like this is a strong argument for maintainability. If you just do this series of instance objects, you get a new type, nobody knows what happens, and how do you even find all of those? Okay, so let's do this. Let's add the GitHub commit page implements page. And so we realized GitHub has more pages, there's issues and pull requests, they also have commit pages. Let's add this here. And now let's follow the compiler errors. The first compiler error is here. The GitHub page record, the commit page record that we're creating that says implements page, immediately gets a compiled error because the compiler says, wait, that type is sealed. Can't actually do that. So then we go with the sealed supertype. So this should be GitHub page, not page, like it should say GitHub page. Okay, so GitHub page can only be a commit page or pull request page, so hence we get a compiled error here. So let's go with the sealed supertype to fix that. So we go to the sealed supertype here, and we add the commit page as a possible implementation. And now, and that's something I didn't tell you before, this thing is no longer exhaustive. Mentioned exhaustive once before. Now I mentioned it again. What does the exhaustive mean? So I get a compiled error here, the compiler telling it is not exhaustive, but what's the concept here? So if you have an if-else-if chain, you can write whatever you want in there, and the compiler has no understanding of whether you cover the whole universe of options, right? If you say, if the string has a length of greater than 4, or else it has a length of 3 or smaller, then you got all cases called greater than or equal to 4. You get my point, right? But the compiler doesn't understand that this if-else covers all cases. If you say greater 5 or smaller 2, there's a gap in between. Nobody knows what's going on there. So if the if-else-if chain, the compiler has no understanding of whether you cover every case. But if you switch over the type, the compiler forces you to do that. So the compiler told before was like, okay, if you switch over page, you need to cover all possible implementations. Or we use a default branch. Those are choices that we have. Right, so if you have a switch that has like, in case it's this type, in case it's that type, and it's all the types, that's good. You can always add a default branch for the rest, but the default branch would mean if I add a new type, I would actually not get a compiler error because, the default branch always grabs every type. So because we did not have a default branch here, and we before did cover all possible implementations of page, we were exhausted before, now we are not anymore. We get the missing case GitHub commit page, so we just add that. And then we look, I just add the GitHub commit page here. And now we're good. Now we're again covering all 5 possible cases. Well, used to be 4, now it's 5. We cover all 5 possible implementations of page. The compiler is happy, but it's still not checked. We had a 6th type, we get back here. So the key is operation is maintainable. You want to switch over a sealed type. You want to enumerate all possible subtypes, even if you have triple or sum. And then you want to avoid the default branch. So on avoiding the default branch, that's sometimes a little bit, So you sometimes have this default behavior. Let's say for a page, you want to pick the emoji. So we issue a picture, a cat for a pull request picture, pick the octopus. And if you have for the GitHub page, I don't care, it's still a page, error page, they don't get an emoji. But so it will be an obvious solution to use default. But again, we use default, avoid the default branch, because if we do a default branch like this, and the GitHub commit page shows up, the compiler says, oh, well, it's exhaustive. The commit page goes into the default branch, right? So we need to avoid it. So we can do it like this. We can simply say error page, I don't need the variable, and an external page, I don't need the variable. So I repeat. It's a big end of the world. But what you can do in Java 21 with the named patterns is you can combine these. So Java 21, you have a good way to combine several branches into one. If all of those branches, you just ignore the variable, you just don't need it. say, okay, for all these other types, this is the default. So you have to basically manually unroll the default so that when a new type shows up, if now GitHub commit H comes in, this is not longer exhausted. Okay, so where are we now? Again, let's take it stock. We separate the operations from the data. You made it so that adding a new operation is fairly easy, right? You just add a new switch somewhere. You say, oh, I have a new subsystem, it gets a page. I switch over the page and I implement the operation. But now if I add a new type, it's a bit more work, right? If I add a new type, I have to go through all the operations horizontally and add the new thing in every switch. Two things I want to say about this. First of all, not all this is the inverse from the object-oriented approach. The object-oriented approach, you add a new type, it's straightforward, you implement the interface, and you just sit down and write all the operations. But if you add the operation, you have to go through all the existing types and add the operations there. So, like, the complexity is literally exactly what I face. You call this the dual of the other problem. That's what I meant earlier when I said that different paradigms have different trade-offs when it comes to which complexity they manage well. Clearly, this is like a minor detail. It's not that much more complex to go across all operations that are added in one place. But you can see how a different approach can lead to different requirements later that progress forward. And the other thing I want to add is that this is the visitor pattern in less painful. This is exactly why we built the visitor pattern. You have a situation where the operations are separate from the data, and where when I add a new operation, I can just do that. But when I add new types, I will get compile errors in all existing operations to fix them. Therefore, we have this whole pattern war. Okay, so that was the data record. Now comes the optional part of the presentation. I will probably use all the remaining 8 minutes. So if you have any questions, I'll be here, and then when the next speaker comes up, I go outside, and I'll be around the conference. I'll be to spot, right? So just talk to me. I'll not spend the rest of the day talking about this, you let me. So I want to push through a few more slides so that you get a little bit more context. But that was like the meat of the presentation, or, you know, the vegetarian was a vegetable presentation. Now let's reflect a little bit. There's a concept called dynamic dispatch. Dynamic dispatch takes an operation and checks which specific operation to invoke depending on the type. You already have that as inheritance as a language feature. If you call a list.add, it checks which type is this actually, and that calls add on that specific type. That's dynamic dispatch. And so if I want to have this as if I need something that uses dynamic dispatch to treat different data differently in terms of polymorphic behavior, as a language feature, I can use with inheritance, and that makes that method part of my API. And that's great in somewhere between 50 and 90% of the cases. But there are cases, and that's again what the virtual paper was put together, where we want to avoid it. So we don't want to make it part of the API. So that it should not be part of the API. Again, the visitor method. That's good, but now it makes the visitation concept part of the API. I work in a code base, but visitor pattern was used a lot. It was the right solution, also very annoying. The visitors everywhere, and always guess like who calls what and where. That especially for newcomers, this indirection is very hard to grow. So now we get a new way of dynamic dispatch, where the methods will become part of the API. The only part that is visible from the outside is the sealed portion. You have to seal the types, do this in a way that's fungible. If you don't seal the types, you always have to add default branches, and that means adding new implementations will always run into that default branch, you don't get compilers. So making it sealed is essential, and that makes it part of the publicly visible API. But that's all. And from there, it's pretty straightforward. So talk about visitor pattern for a while. That's also an interesting thought. I'm not sure about 100% subscribe to this idea, but I agree it makes sense to me. The theory here is that design patterns make up for gaps in the language. And I feel like the strategy pattern is a good example. Now, I got told out the last time I gave this presentation that this is not actually every always a strategy pattern. I don't care, but I think it is. But if it's not, it's some kind of pattern. Point is, the strategy pattern where you pass behavior into other codes, that used to be like a big thing, right? Oh, I need to pass behavior. I want to create this interface. I want to create these implementations. Like I didn't get off 4 thing, I can go on. That's how it felt in the strategy pattern. But not every time you pass a lambda, a stream API, it's always, again, it's the pattern. Maybe it's not this one. It's a pattern. Do you think every time you pass the lambda that you're now doing a pattern? No, it's just the language feature, just what the language allows you to do. So in that sense, pattern matching does the same for the visitor pattern. This used to be like a thing that you would really realize at some level, oh, I need this. So I reread the game of Porto, the book for our visitor pattern, and I implement it. And now we just end up doing it. Where can you do it? Ad-hoc data structures, complex return types, and even complex domain types. I'm going to give you an example for each. Let's start with this one. This is an example of one of earlier action to need mutability. I was in a situation where I needed a local type. This code parses a page, right? And then when it has the content of the page, it goes to the content looking for links. And it puts those links somewhere, right? And I needed that. Well, together I need the incomplete page, which have all the data except the links. And I need a mutable, not immutable, a changeable set of links. And I can just put the links in, right? It's just URI instances. So, I create a type record page with links. And everything that's down here, that's just to make it nicer for myself. I wouldn't have to do this. I could just have record page with links, there's a page at links, and there you go. This would be a named tuple. It's a tuple, but it has a good name. The accessors are of course get 1 and get 2 or something. They're all page and links. And again, I just put in a little bit of extra effort to make sure I don't create false data, like I don't have a null page or null links. I'll create a mutable copy of the links set, so I can always edit this. I even went through the effort to edit a new constructor that starts with the empty set. So that's all. Just the first line will be enough though. So if you have a situation where you feel like, oh, I have this piece of data, that piece of data, I just want to keep this, just drop this together for a couple of lines of code, or create a record. Very straightforward. We could do the whole sealed types and implementation thing pretty well too. So this works great for return values that be constructed soon. Let's start at the bottom. I have a find user method that takes a username and returns a match of a user. Match turns out to see the interface, and the implementations are none. One didn't find one, obviously. It's an exact match, always like a bunch of almost matches. This is what it looks like to call it. I find the user tree though, I switch over the result, place none, case exact, case hypothesis. And I would argue this code is super readable. Like if you read this code, you immediately say, oh, I'm finding something, and in case I did not get a result, I'm doing this, to I get the exact result, I'm doing that. It's also easy to write. You do a find user, you know this is a sealed interface, you tell your IDE to put a switch with all the possible implementations there, and then you know which case you're in, right? If you write this part here, you know exactly that you're in the none case. But you can also use this for more complex domains, which is what we've been doing on the example page. Page was terribly complex, right? But it was like a set release of this entire little demo project that I built, and it's separate here as well. There's a concept code I would write data types, which I'm going to skip past. If you ever heard that before, or if you're interested in that, we have that now in Java. Bunch of programmers like data, let me know what that's into. Yeah, so records are all types, sealed types, some types, and combining these ways to put stuff together easily and to model alternatives. It's very powerful. It's simple but powerful. Now, those of you who do functional programming might have wondered, like, wait, you talk about immutable data structures or operations that live in elsewhere. Call it functions even. Isn't it just functional programming that you talk about? Then, yeah, kind of. So, I put we to. It's very close to functional programming. I would say there's a little bit of difference in emphasis. Functional programming says everything is a function, so you want to focus on creating and composing functions. Whereas the data-oriented programming more of data first. So if you have a trade-off between getting the function right and getting the data right, I wouldn't say that these two paradigms give you different emphasis. But if object orientation is here and functional programming is here, then data-oriented programming lives here somewhere. And so it's definitely much closer to that. But object-oriented programming is not that. It's still a good default to turn large problems to smaller problems. But once you have a smaller problem, or a problem that mainly deals with handling outside data. When you are in a case where you feel like the data and behavior should not be on the same types, in those situations, consider using data-oriented programming. Now, people like complex solutions to complex problems or in functional programming. Clearly, that's possible. Fast object-oriented programmers, it seems a little far-fetched or a little difficult to get there, though. And data-oriented programming gives us a specific circumstance to which we can try and build things more. Okay, this The summary, use classes to present data. Data as data with records. The alternative with sealed classes. And then use the methods elsewhere to model the behavior. Do an exhaustive switch without default. Use declamation to structure polymorphic data. Those here, all those are links if you want to learn more. Thank you very much for your attention.